Welcome back. It's time to discuss hypothesis testing, which is a major topic, some would say the major topic, in inferential statistics. Santa Claus is here to bring us his ho-ho-hos, but to balance him, Krampus is here as well. Now everyone knows Santa, who brings presents to good boys and girls at Christmas, but not everyone knows about Krampus, who according to certain Central European legends, brings punishments to bad boys and girls at Christmas. And if Santa's the man for ho-ho-ho, we'll turn to Krampus for a hearty ha-ha-ha! So, what is all this about hoing and hawing? Well, every statistical hypothesis test involves a ho and a ha, which stand for two competing hypotheses. The ho, which is actually read H sub 0, is called the null hypothesis, and this is the hypothesis that everything is status quo. The null hypothesis always says that everything's as expected, there's nothing interesting going on, move along folks, there's nothing to see. In contrast, the ha, which we read H sub a, is what's called the alternative hypothesis. The alternative hypothesis denies the null hypothesis, often in a particular direction. So if the null hypothesis is everything is status quo, the alternative hypothesis might be no it isn't, it's worse, or no it isn't, it's better. This is what I mean by saying that it often denies the null hypothesis in a particular direction. But the alternative hypothesis could also deny the null in an undirected way. If the null says everything is status quo, the alternative could just be, oh no it isn't. This will be clearer when we look at some examples. Here's one possible duel between a ho and a ha. Suppose we're doing medical research and we want to test a potential new medication, a pill that we think will lower patients' blood pressure. In this case, our null hypothesis will be that the pill has no effect on blood pressure. Everything is status quo, the pill changes nothing. In contrast, our alternative hypothesis will deny this by claiming that the pill reduces blood pressure. Simple enough. For another example of competing hypotheses, suppose we have a coin that we think is biased towards heads, and we wish to test this. In this case, our null hypothesis would be the coin is fair. Nothing unusual here, just a fair coin like other coins. The alternative hypothesis denies this, claiming that the coin is biased towards heads. And now for our last example, we'll return to the Guinness factory where we spent some time in our previous lecture. The machines in the factory are supposed to put 12 ounces of stout in each bottle. Suppose our job is quality control. We want to test to ensure that this is actually happening. But if there's a problem, we have no reason to suspect that it will be in one direction or the other. Maybe the bottles are being underfilled, or maybe they're being overfilled. One thing we might do, of course, is construct a confidence interval for the mean volume of stout, but another approach is to do a hypothesis test. In this case, our null hypothesis would be bottles contain 12 ounces, as advertised. And our alternative hypothesis would simply be bottles do not contain 12 ounces, with no direction indicated. Okay, so far so easy. We've really just introduced some new terms. But in a moment, I'll introduce the logic of hypothesis testing itself, which is quite tricky, especially when you first meet it. To pave the way, I want to point something out that may help a bit. In all the examples we have here, it is the null hypothesis that states something precise, while the alternative merely says, I don't think so, and at best indicates a mere direction, with no precision attached to it. Take the first example about the pill. The null hypothesis is boring, but precise. It suggests that if someone takes the pill, the effect we should expect to see on that person's blood pressure is precisely 0. The alternative tells us that blood pressure will be reduced, but by how much? A little? A lot? Who knows? Same story for the coin. The null hypothesis is boring but precise. If the coin is fair, then the probability of heads should be precisely 50%. The alternative is vague. It suggests a bias towards heads, but how substantial is that bias? Will it come up heads 80% of the time? Or is it just a slight bias, coming up heads maybe 52% of the time? And of course, the same pattern holds for the Guinness example too. But why does the precision of the null hypothesis matter? It matters because we need precise information to do probability calculations. Without that precision, we can't calculate. For example, suppose I'm going to flip a coin 3 times and I want to know the probability of getting 3 heads. If you know the coin is fair, then you can compute this probability easily. It's 0.5 cubed, which is 0.125. That is, if the null hypothesis is true, you can compute the probability we want. However, if the alternative hypothesis is true, then you don't have enough information to compute the probability. Maybe it's 0.8 cubed, Or maybe it's 0.52 cubed. Who knows? For this reason, whenever we do a hypothesis test, we can't test the alternative hypothesis directly. Instead, we do something very sneaky and test it indirectly. Namely, we test the null hypothesis, and if our calculations suggest that something looks fishy, then we'll reject the null hypothesis in favor of the alternative. That's the basic idea. Here's a bit more detail on the indirect logic of hypothesis testing. Once you've set up your competing hypotheses and gathered your data, there are really just a few steps. First, we suppose, for the moment, that the null hypothesis is true. As we've just indicated, this will let us compute the probability that we'll need in the next step. The second step is to compute the so-called p-value associated with your hypotheses and data. Okay, but what is a p-value? Brace yourself. The p-value is the probability of seeing data at least as extreme as yours if the null hypothesis were true. I cannot emphasize enough how important it is to thoroughly understand the definition of a p-value. It is very easy to misunderstand. The p-value is almost certainly the single most abused statistic of them all, sometimes deliberately, sometimes unintentionally by people who don't really understand it. The third step is to interpret the p-value. Doing this will let you decide whether it is reasonable to reject the null hypothesis in favor of the alternative hypothesis. No doubt this sounds confusing. That's because it is, at least at first. A concrete example or two should help. So, let's consider a coin. Suppose we have reason to believe that this ancient Roman denarius, which was minted in 44 BC, is biased towards heads, namely the head of Julius Caesar. To test this, we set up a familiar pair of competing hypotheses. Our null hypothesis is that the coin is fair. Our alternative hypothesis is that it is biased in favor of heads. Now we need to gather some data. Let's say that to test these hypotheses, we'll flip the coin 10 times. Now that is far too few flips for a real test, but the goal here isn't realism. It's to explain the ideas of hypothesis testing in a simple setting. Anyway, we flip it 10 times and get 7 heads. Now we have our competing hypotheses and our data. So, to test our hypotheses, to determine whether our 7 heads are compelling evidence of a biased coin, we need to follow our 3-step plan. First, we need to suppose for the moment that the null hypothesis is true. If the null hypothesis is true, then the coin is fair. And if the coin were fair, the thinker thinks, we'd expect 5 heads when we flip it 10 times. Of course, we know that we won't always get 5 heads. That's just the long-run average. Still, we flipped 7 heads. So, should I be suspicious? Is this a bit too extreme for a fair coin? And with this thought, the thinker proceeds to the second of our 3 steps and asks, well, what's the p-value here? To answer this question, we'll need to remind ourselves of the definition of a p-value. A p-value is the probability of seeing data at least as extreme as yours if the null hypothesis were true. So, when the thinker wants to know the p-value for his hypothesis test, he wants to know what's the probability of at least 7 heads if the coin is fair. Now this is the kind of question that we know how to answer. If we flip a fair coin 10 times and let x be the number of heads, then x is a binomial random variable, and you learned all about those in a previous video. Now the p-value we want is the probability of getting at least 7 heads. That is, the p-value is the probability that x is at least 7. There are many ways for x to be at least 7. It could be exactly 7. It could be 8, or 9, or 10. If we find all these individual probabilities and add them up, we'll get the result we want. Each individual probability is easy to find by going through the usual binomial song and dance. The details of those calculations are not what is important here, and in practice this calculation would be done by a computer anyway. Once we've done the calculations, or had a computer do them for us, we'll find that the p-value we seek is approximately 0.17. Good, we have our p-value. Now we can forget about the details of computing it and think about how to interpret it, which is the third and final step in our hypothesis testing procedure. So how do we interpret it? Let's remind ourselves once more of the crucial definition. The p-value is the probability of seeing data at least as extreme as ours if the null hypothesis is true. So our interpretation of our p-value of 0.17 is this. If the coin is fair, we'd expect to see 7 or more heads about 17% of the time. Now 17% is about a 1 in 6 chance, so our data, those 7 heads, really can't be considered all that extreme or suspicious for a fair coin. Based on this data, it's certainly plausible that the coin is fair, and that this is just one of those not terribly rare instances in which Lady Luck produces 7 or more heads on 10 flips of a fair coin. What we've seen is no rarer than rolling a 6 on a die. Hence, we don't have enough evidence to reject the null hypothesis. Note the language here. We haven't declared the null hypothesis to be correct. We've just failed to reject it. This is rather like a court of law in which a defendant is presumed innocent until proven guilty and is eventually declared either guilty or not guilty. When we do a hypothesis test, we effectively put the null hypothesis on trial. We initially give it the benefit of the doubt and assume it's true, and after weighing the evidence, we either then reject it or fail to reject it. Now, in this example, the p-value was 0.17, so we did not reject the null hypothesis. If the p-value had been lower, we might have. Indeed, as the p-value goes down, our willingness to reject the null hypothesis goes up. The ideas of hypothesis testing were introduced by Ronald Fisher, one of the founding fathers of statistics. Fisher suggested the following rule of thumb. Reject the null hypothesis when p is less than 0.05. It is worth noting that Fisher did not intend this rule of thumb as gospel, but many have taken it as such. At any rate, this is, for better or for worse, a common convention in many fields that make use of inferential statistics. With this in mind, let's return to our coin example, but let's say we now have more extensive data to analyze. Namely, we flip the coin 100 times and get 70 heads. Now we want to carry out our hypothesis test with this new data. As in every hypothesis test, we begin by assuming, for the moment, that the null hypothesis is true. Well, if the coin were fair, we'd expect 50 heads. We got 70. Should I be suspicious? Asks the thinker. Is this a bit too extreme for a fair coin? Such questions lead us to our second step. We ask, well, what's the p-value here? And I'll remind you once again, because it is such a crucial definition. The p-value is the probability of seeing data at least as extreme as yours if the null hypothesis were true. So in this particular case, the p-value answers the question, what's the probability of at least 70 heads if the coin is fair? This is a question we can answer after I clean up some of this clutter. If we flip a fair coin 100 times and let x be the number of heads, then the p-value is the probability that x is at least 70. Since x is a binomial random variable, we can compute this. You certainly don't want to do it by hand, and in practice, we'd have a computer do it for us. Let me emphasize once again that for the most part, actually computing the p-value is not our interest in this lecture. Our concern is with understanding them. Anyway, it turns out that the p-value here is about 0.00004. This is tiny. Let's interpret it. What this p-value tells us is that if the coin is fair, getting 70 or more heads in 100 flips would be exceedingly unlikely. It would happen only about 4 times in every 100,000 trials. That is, we'd expect to see something like this only once every 25,000 times that we play this game of flipping a fair coin 100 times. So, this leaves us with 2 possible explanations for our data. The first explanation is the coin is fair, and we've just witnessed a very rare event. If we accept this, then we would be retaining the null hypothesis. Or the second possibility, which feels much more reasonable here, is simply that the coin is not fair. So what do we do? Retain the null hypothesis or reject it? It doesn't take much further thought for the thinker to recognize that the p-value here is minuscule, far below the usual 0.05 standard, so he shouts out decisively, "I reject the null hypothesis." And that's that. By now, I hope you have a basic understanding of the strange indirect logic of hypothesis testing. We suppose the null hypothesis is true, Then find the p-value associated with your data and hypotheses, and finally interpret it, which will help you decide whether to reject the null or not. And we might as well bring Fisher back in to remind us of his rule of thumb, and to introduce some common, but not very good, terminology. If p is less than 0.05, we usually reject the null hypothesis and say the findings are statistically significant. This notion of statistical significance has led many people astray. All it means is that p is less than 0.05. It sounds like it should mean something else. It does not. I'll apply 2 warning labels to this troublesome phrase. First, statistical significance is not the same thing as practical significance. To see why, let's consider another example of hypothesis testing. This one will be about a new pill that medical researchers think will reduce systolic blood pressure. In this case, our null hypothesis will be that the pill has no effect. Our alternative hypothesis will be that the pill reduces systolic blood pressure. We'll need to gather some data. In our study, we give the pill to 400 randomly chosen people, measuring their blood pressure before and after. For each person in the study, we'll record the change in systolic blood pressure. Let's say that when we average those 400 changes, we find that the mean change in systolic blood pressure is -1 millimeter of mercury. Millimeters of mercury is just the weird units used for blood pressure. That is, one person's blood pressure may have dropped by 10, another's may have been lowered by 3, someone else's went up by 5, and so on and so forth, but the mean of all those changes was a reduction by 1 unit. Moreover, let's say that the standard deviation is 5 units. Now we're ready for our hypothesis test. First step, imagine the null hypothesis is true. If the pill had no effect, we'd expect the mean change in blood pressure to be 0. This isn't what we saw in our study, so the question arises, is our data, a mean reduction of 1 unit, too extreme for a pill with no effect? Should we be suspicious? Well, what's the p-value here? And I'll make a nuisance of myself by reviewing the definition once again. A p-value is the probability of seeing data at least as extreme as yours if the null hypothesis were true. So in this example, the p-value is the probability that x bar is less than or equal to -1, where x bar is the mean change in systolic blood pressure of 400 randomly chosen people. Now this is something we can calculate. First, let's rearrange this a bit. We're working with x bar, so let's begin by noting that x bar is normal by the central limit theorem. Moreover, this analysis is all taking place in the thought bubble in which the null hypothesis is true, and in that setting, the pill has no effect. So the mean of x bar, the expected value of x bar, is 0. As for the standard error, we know that is the standard deviation of x itself over the square root of the sample size. Here, that will be 5 over the square root of 400. Since the square root of 400 is 20, that's 5 over 20, which reduces to 1 over 4. Now we're in business. The p-value is the probability that x bar is less than -1. But x bar is a normal random variable, so we can standardize this and rewrite it as the probability that z is less than or equal to -4, since -1 is 4 standard errors below the mean of 0. Wolfram alpha tells me that this probability is about 0.00003. Very, very low. If the pill has no effect, we'd expect to see results like ours only 3 times in every 100,000 experiments. It's enough to make the thinker break out of his reverie and blurt out, "A statistically significant finding! I reject the null hypothesis!" And just when he's about to alert the FDA that he's developed a drug that has been shown in a statistically significant test to reduce blood pressure, and which will therefore save countless lives, Ronald Fisher enters the room to say, "Yes, these are statistically significant findings, O thinker. But are they practically significant?" The honest answer to this question is almost certainly no. True, this drug does genuinely seem to reduce systolic blood pressure, but only by a tiny, tiny bit, namely by an average of 1 millimeter of mercury, a reduction far too small to have any practical effect whatsoever on a person's health. This is probably not the drug to which we should be devoting our precious research hours and dollars. Okay, let's look back again at our hypothesis testing summary. You now understand the first warning label. Statistical significance, i.e. a low p-value, is not the same thing as practical significance. But I need to attach a second warning label about statistically insignificant results. Suppose you do a hypothesis test and the p-value is fairly high. Say it's 0.15 or 0.47. You clearly won't reject the null hypothesis on the basis of that p-value, but does your data's failure to reject the null hypothesis imply that the null hypothesis is probably correct? No, this does not follow. I'll explain why after I affix this next warning label. Statistical insignificance is not evidence in favor of the null hypothesis. You've actually seen an example of this already when we discussed flipping that ancient Roman coin. Recall that our null hypothesis was that the coin is fair, while our alternative hypothesis was that the coin is biased towards heads. Recall also that we collected data on this coin twice. On the first occasion, we flipped the coin 10 times, obtaining 7 heads and 3 tails. The p-value associated with this data and these hypotheses was 0.17, which is statistically insignificant. Once again, be sure you understand this p-value. It tells us that if the coin were fair, we'd expect to see results at least this extreme 17% of the time, which means that our data wouldn't be all that surprising for a fair coin. That being so, we shouldn't reject the possibility that it is fair. But this is not evidence of the coin's fairness. In fact, let's just say that I happen to know from my godlike perspective here behind the microphone that this coin is biased towards heads, and that every time we flip it, there's actually a 70% chance of heads. I know this, but our researcher doesn't. And while the researcher says, 7 heads wouldn't be too surprising for a fair coin, so I'd better not reject the null hypothesis, I just laugh because I know that the coin isn't fair. And I laugh especially hard because this coin is even trying to show the researcher its true colors by coming up heads precisely 70% of the time. How on earth could 70% heads count as evidence in favor of the null hypothesis, which states that the coins should come up heads only 50% of the time? This may sound obvious, but people often make this kind of mistake, so I'll repeat the warning. In and of itself, a statistically insignificant result is not evidence that the null hypothesis is true. It's just a sign that our data wasn't strong enough to warrant rejecting the null hypothesis. In this particular case, the data wasn't strong enough simply because there was so little of it, because we only flipped the coin 10 times. In contrast, when we flip the coin 100 times, obtaining 70 heads and 30 tails, which is the exact same ratio of heads to tails that we saw before, now our evidence against the null hypothesis was much stronger. As we've discussed before, anything can happen in the short run, like a fair coin coming up heads 70% of the time, but not so in the long run, for there, the law of large numbers takes over. Consequently, our p-value for this second data set dropped all the way down to 0.00004, a statistically significant result. Okay, I've already been compelled to affix 2 warning labels to the framework of hypothesis testing and p-values, and I could plaster even more warnings on there. The problem is not just that college students trying to satisfy their math requirement tend to misinterpret p-values. The problem is that many professional researchers misinterpret them. And this problem is massive enough to prompt articles like this. Scientists rise up against statistical significance. Over 800 scientists call for an end to hyped claims. These would be of the p is so low that this must be important variety, and dismissal of possibly crucial effects. This would be mistaking statistical insignificance for evidence of the null hypothesis. This is in Nature, by the way, widely reputed to be one of the premier scientific journals. Also in Nature, a proposal to redefine statistical significance by changing the threshold for significance from 0.05 to 0.005. Or here, in Science News, a story about a psychology journal that actually banned the use of p-values in its articles because its editors thought they were so routinely abused and misunderstood. Or you might encounter articles like this in Science-Based Medicine, warning readers to beware the p-value. In 2016, even the American Statistical Association had to issue a statement about the abuse of statistical significance and p-values. Indeed, the problems are so severe that it is not uncommon to see road signs like this. Seriously, though, P-values certainly do have their uses, but they are easy to misuse, easy to abuse, easy to misinterpret. So be sure you understand precisely what a p-value is, since, for better or for worse, they are pervasive in the scientific, medical, and social science literature. One of the best warnings about one of the many ways in which p-values can be misused or misinterpreted comes from Randall Munroe's webcomic XKCD. If every student who passes an elementary statistics course comes out of the course understanding this particular strip that I'm about to show you, the world would be a better place. So, here we go. "Jelly beans cause acne," exclaims the ponytailed woman to a man who seems to be the director of some sort of lab, because he immediately cries, "Scientists!" who don't want to be bothered because they're too busy playing Minecraft. But their boss insists, "Investigate!" Fine. The scientists do investigate and report back. We found no link between jelly beans and acne. P was greater than 0.05. That is, in their experiment, the data was not strong enough to warrant rejecting the null hypothesis that there is no link between jelly beans and acne. "That settles that," says the lab director. But Ponytail is having none of this, and changes her hypothesis. "I hear it's only a certain color that causes it." Note that she doesn't specify which color. "Scientists!" shouts the lab director, and the scientists lament that they are still being kept from their video game. They get back to work on the jelly bean study, and eventually report their results. "We found no link between purple jelly beans and acne, P greater than 0.05. Then they turn their attention to another color. "We found no link between brown jelly beans and acne, P greater than 0.05. And after that, another test. "We found no link between pink jelly beans and acne. The same happens with blue, teal, salmon, red, turquoise, magenta, and yellow." I should mention here in passing that scientific journals tend not to publish many papers that turn up statistically insignificant results, since these tend not to be very exciting. So our two scientists here may be disappointed that they probably won't even get a published paper out of this work. But nonetheless, they persist, and find no statistically significant link between acne and gray jelly beans. What flavor are those, I wonder? Same story for tan and cyan, whatever that is. But then, lo and behold, we've found a link between green jelly beans and acne, P less than 0.05, a statistically significant finding. "Whoa!" exclaims the lab director. And they continue, finding no link between acne and yellow jelly beans, nor with beige, lilac, black, peach, or orange jelly beans. So what comes of all this? A result that would make anyone who understands p-values hang his head in shame. But in comic form it just makes us laugh with rueful recognition. A scientific article gets published which makes no mention of any of the 19 insignificant results. This article ultimately gets filtered down all the way down to the level of the mainstream media until we see in the news, "Green jelly beans linked to acne." Why is this bogus? Well, note that in this cartoon, the researchers have adopted the usual convention for statistical significance. Reject the null hypothesis when p is under 0.05. The null hypothesis here is that consumption of jelly beans, of whatever color, is unrelated to acne. Now, if we adopt this convention, and the null hypothesis happens to be true, then by chance variation alone, we can expect to see data that is extreme enough, even though the null hypothesis is true, to set off the significance alarm 5% of the time. These false positives are one reason why it is so important for statistical studies to be replicated before we consider them fully legitimate. Well, 5% of the time is the same as 1 in 20. Our jelly bean researchers did 20 different tests, so even if the null hypothesis is true and there is no connection whatsoever between acne and jelly bean consumption of any color, we would expect one of those 20 tests to produce a p-value below 0.05 by sheer chance alone. And indeed, we got one. This is not, in fact, evidence that green jelly beans cause acne. Most likely, this is just one of those 1 in 20 times when we get a false alarm for significance. Replicating the study with green jelly beans would almost certainly show as much. And when attempts at replication fail to show the same thing, that usually doesn't get reported. All right, that's all for your introduction to hypothesis testing and p-values. They are powerful but dangerous tools. Be careful out there. And remember, Santa himself urges you not to use p-values unless you really understand them. If you abuse p-values, he will have no scruples about leaving you to Krampus, who likes nothing better than stuffing naughty misusers of statistics into his basket.